Hello everyone. Welcome to the next lecture, the second lecture on an introduction to RF microelectronics. So in today's lecture we'll look at the applications of RF microelectronics, and we'll see the different trade-offs which we encounter when designing systems in the RF domain. And we'll also go through some nomenclature which is very prevalent in this field. So to start with, let's look at the relevance of RF microelectronics. So we find RF everywhere, from our laptops all the way to our cell phones and printers, and nowadays our smart TVs, even our microwave ovens. Now this is a recent addition, and there have been many new devices which are part of what we call a smart home. So you'll have many devices like the recent uh, Amazon Alexa, right? And you have what's called Google Nest. So these devices then in turn connect to a lot of smart things which have been available in the market recently, including say coffee machines, including refrigerators, and then you also have you can have light bulbs. You can have smart light bulbs which you can switch on and off using your phone. They also connect wirelessly to your routers. Uh, then many very simple applications like toasters. There are smart toasters which again become a part of your what they call a Google Home or an Alexa system, and then you have a smart home, and you can control all of these appliances wirelessly. So an increasing number of devices are now available which have a wireless function, and it's going to be increasing with advancement in technology. So as we go on increasing the speeds, as we go on increasing the bandwidths, you'll see more and more devices being able to use this. And it has been like this for a long time, since IoT came into being. So all of this is part of IoT, and an Internet of Things, which enables you to control different things from the palm of your hand. And all of this basically, yeah, depends on RF. So at its very core, it's just RF microelectronics doing the work, right? So yeah, so high-speed wireless links, they which allow connections between devices and appliances, and uh, we the main concepts would be the same for both wired and wireless applications. It's just that the wireless applications will have use of some antennas and some EM theory, although we won't be going into that. That's in itself a different field of study. But as far as the generation of those signals is concerned, it doesn't matter if the signal is to be supplied to a wire or if that signal is to be supplied to an antenna. So from that perspective, RF microelectronics does not really distinguish between wireless and wired systems. Um, uh, but the frequencies which we'll talk about will definitely be the ones which are commonly used in the wireless domain. So yeah, and as we can see, I mean the size of devices and the complexity of devices has been shrinking, right? If you compare an old Motorola car phone, which is how radios basically started, this was one of the oldest applications of you know, wireless communication was by Motorola, which they enabled customers to communicate using their phones in their cars. And then this was 1940s, and we moved to 1973, and then we have our first handheld phones, which I mean are really the ancestors of the the modern mobile phones or the cell phones, the smartphones. And if we look at the speeds and the technologies used for different generations of wireless communications, we'll see a drastic change in the speed. We start with 1G, which was in the 1970s, and a speed of about 14 kbps, and which is even slower than what we had for wired systems back in the day, which was 56 kbps for modems, right? And then you have 2G systems, which were up there until very recently. We had 9.6, and then up to 14.4, and then better 2G systems, right? We had about 170 kbps, which was very common. It was called GPRS, right? And GPRS, it came at a time when the when mobile phones were penetrating, into the market, and you could find mobile phones everywhere, and GPRS was a huge selling point for phones. And then came 3G again with a huge media entry, and you could see advertisements all over the place. 3G and high-speed internet. Back in the day, this was big talk. 3G and 3.5G and HSPA. This 3G and 4G, which was there after 2010. This really revolutionized how we interact over the internet, and so all the social media companies, all the uh, entertainment networks like Netflix or Amazon Prime, YouTube, see, all of them flourished because of these key technologies, 3G and 4G. Going forward, and currently, the world is moving towards 5G, and tests are being conducted by Airtel in India, and it has been deployed in some form around the world in the US or some European countries, though not in its true form, but in some form it has been implemented by some carriers, and the goal is to get a LAN-like connectivity in the wireless medium. So a 1 to 10 Gbps, which is typically what gigabit LAN is. So you want to get that performance over a wireless medium, and this is in itself is a very challenging field. And going forward, we are looking at future technologies which are 6G. Again, some of the countries in the world have already started working towards 6G, and 5G is yet to roll in India, but we can expect a rollout maybe next year in 2022. And there are already many companies working towards 5G, and there have been trials across the country, and it looks promising. So we can expect 5G to come soon. So all these different technologies have progressively improved the speed of communication of these devices over the internet. Now, if we look at the devices, the actual devices, the transistors, if we look at the transistors which are part of these devices, you'll see that the technologies changed very rapidly from the 90s to the 2000s. So we started with a zero point 0.5 micron MOSFET, right? We started with MOSFETs, 0.5 micron MOSFETs around the 90s, and then we had a 40 nanometer technology around 2010, and today we are moving down to 7 nanometers. We're moving down to 5 nanometers. So we are increasingly able to shrink our devices, and because we're able to do so, we're able to increase the frequency of operation for these devices. So FT is the unity gain frequency, and it is the frequency at which the gain of the transistor or the mod of its H21 becomes unity. So the frequency So this is basically the frequency at which mod of H21 becomes 1. So that is your Ft. And Ft is proportional to the transconductance of a device, and it is inversely proportional, for MOSFETs at least, it's inversely proportional to the gate capacitance of the device. So as long as you have smaller devices, if you go on shrinking your device length, you'll see that you're able to decrease the CGS, and you're also able to increase this GM. So if you're able to decrease CGS, you're able to increase FT. If you're able to increase GM, you're also able to increase FT, and that's what we are seeing. As we go towards smaller gate lengths, we see an increase in the FT, but then there's a limit to how much you can go on reducing CGS, right? So if you then move back to FinFET technologies, which are the current technologies, so FinFETs, now instead of a planar MOSFET, you have a device which has a gate on 3 sides. Then again, your parasitics start to become significant, and you're not able to shrink CGS as you had been able to previously, and you see that the increase is not as steep as it used to be. And going forward also, it's not going to be as steep as it used to be, moving from 0.5 to the nanometer, moving from the micrometer to the nanometer range. So this steep slope was because of the significant change in the capacitances, and we're not able to do that anymore because going down, the changes in CGS are not that significant anymore. So scientists are trying to find new ways to improve FT. We are trying to find faster devices. We're trying to find devices with higher GMs, and the search for a proper device, for the perfect device, is always, it always goes on. Now, and the research in this field has also been going up. If you look at the papers in RF and wireless, you'll also see good increase over the years, and people have been more interested in RF and wireless communications. And then scaling has also helped us manage costs. So when you're able to scale, you're able to pack more devices on a given wafer area, and that reduces the costs. That has really led to the widespread use of microelectronic devices all over the world. Moving on to the design part. Now, RF design in itself is based on many different fields. It's based on communication theory. It's based on random signals. It's based on noise. So you need to understand how noise and random signals work. You need to understand different architectures from different transceiver architectures and how they affect performance. You need to understand IC design, and that involves the understanding of devices, that involves the understanding of circuits. Again, transceiver designs and transceiver architectures and circuits are closely related. You need to understand CAD tools. So if you're making an RF circuit and you're then putting it on a package, say for example a QFN package, you're putting your chip out there on a QFN package. You need to understand what are the different parasitics, on a QFN package, what are the different parasitics and how those affect your performance. So you need to have CAD tools so that you can perform these simulations and you can understand the impact of these parasitics. Or you fabricate something and then you place it on a QFN package. You have to use bond wires, right, in order to connect the actual chip with the pads. So there are a lot of bond wires involved, and you need to understand the impact of those parasitics on your device performance, on your circuit performance. So for that, you need to have different CAD tools so that you can perform those simulations. And then you need to understand wireless standards. So there are different IEEE wireless standards. Uh, so for Wi-Fi, you might have heard of Wi-Fi B. You might have seen something like this, BGN. So different wireless standards talk about how things should be in the physical layer of communications. Then for newer technologies like 5G, increasingly depending on multiple access protocols. So MIMO is a big buzzword in 5G. It's multiple in, multiple out. Uh, so how to enable multiple access on your device. And then signal propagation through space, signal propagation through your chip itself, signal propagation through wired media. You need to understand these things well, and you need to take them into account when designing your circuit. And then if you're doing antenna design, if you're doing passive microwave circuits, you need to understand microwave theory well. So overall, you need to understand different fields from the electrical and electronics engineering disciplines, and only then can you start a true RF design. And that's what makes this challenging, and that's what makes it fun and interesting. Now there are different trade-offs which you need to take care of, and let me add to this. In fact, there is one more trade-off. Let me see how to include stability as well. Yeah. So now there are different trade-offs when you're designing RF networks or RF circuits. You have to consider noise. If it's an LNA, you have to consider low noise. If it's a power amplifier, you have to consider the power considerations, the power requirements. And these things often reduce as you try to increase the other parameter. For example, if you try to go for a high frequency device, you'll have challenges getting a high power out of the device. So for typical silicon devices, they are limited in terms of the power they can deliver at high frequencies, and that is why we started moving towards other technologies. So we started moving towards SiGe. We started moving towards LDMOS devices. We started moving towards GaN devices, right? So GaN is a recent technology, and these devices can provide you high powers at high frequencies. And we are still, and the search goes on. I mean, we always try to get the best, and the search still goes on. We are looking at new devices. We're looking at diamond, we're looking at silicon carbide, although these devices are not good at high frequencies. They're not good at high frequencies, but they do provide high power levels, right? Then there are some devices like in-GaN based devices, which are good at very high frequencies, but not so good at high powers when compared to diamond and silicon carbide. So they're good at high frequencies, but not so good at high power levels. Then we try to do some things to make them good at high power levels. So the research is going in both directions. Research is going on in both directions, and both these devices find applications in their relevant fields. For example, you'll see power devices which don't require high frequency applications. So power applications are increasingly being researched using diamond or SiC, or there are other devices like gallium oxide. So we are trying to make new devices using these materials. And then at the towards the high frequency side, we're looking at in-GaN or similar materials, and we're trying to improve their power performance. And that's again a field of research that's going on. So overall, as I was mentioning, there's always a trade-off between different metrics. So if you want high frequency, you might have to sacrifice some gain, or you might have to sacrifice some stability. If you want high gain, you might have to you might end up having an unstable device. But if you want a stable device, you might have to sacrifice some gain. And so we have all these different metrics which form a trade-off, and you have to be able to get an optimum design out of your specifications while trading off these different metrics. Again, this is something which makes it challenging and exciting. So what's the big picture? The big picture is that in RF communications, you have two key components. You have a transmitter side, you have a receiver side, and at the transmitter side, you need something to deliver the power, right? So you need something which is able to deliver power, and that's what a power amplifier is. So at the transmitter side, you have power amplifiers, and at the receiver side, after the signal has traveled, it has suffered some attenuation, right? It has suffered some attenuation, and that attenuation as well, so there's attenuation as well as there's some noise. As it is traveling through the system, there's noise, so there's interference. So there are two things: there's noise, there's interference, and these two things deteriorate the signal as it reaches the receiver. So now you need a device which is able to get the best signal out of the medium. So what you need is a device which introduces little or no noise by itself. So the goal is that this device should not introduce any more noise to the signal. So it should receive the signal as it is. So the goal at the receiver section is to have no noise. The goal is to have no noise, but then you cannot have a zero noise system. So what we aim to achieve is a low noise amplifier which can receive the signal which is full of noise, which is very low in amplitude because it has been attenuated over a long distance. Now the goal is to get this and to amplify this. So you have to get this signal which is small, and then you have to amplify it without amplifying the noise. You have to amplify it to a significant level so that you're able to extract information out of this. So then that is the receiver section. So the key component for a receiver section is a low noise amplifier. You need to have a low noise amplifier for the receiver section. For the transmitter section, you need to have a good power amplifier, and the metrics which we use to design power amplifiers are one, it's the power levels. You should be able to get good power levels out of your power amplifier. You should be able to get linear power, right? You should not have non-linearities. If the input is a sine wave, you expect a sine wave to come out. You'll try to keep the system as linear as possible. So power amplifiers, since they supply high power levels, tend to be non-linear. So the goal is to keep them as linear as possible, or to reduce the non-linearities in the power amplifiers. We'll see how we measure or how we characterize non-linearities. We'll see them in upcoming lectures, and we'll see how to control non-linearities in power amplifiers as we go down the course. So this is a typical RF transceiver. Like we mentioned, there are two key components, a transmitter and a receiver, and when you combine them in a system, so you have a TX and you have an RX, and then you have maybe a switch. You have a switch, right? You have a switch which controls the two, or which switches between the two, and then this entire system Now it's called a transceiver, right? So now if you have a transceiver, it has different components. You have antennas, then you have let me add another block. You have switches. Then you have LNAs and PAs. Then you also have down converters and up converters. Yeah, and in order to make them work, you need oscillators. So there are oscillators. Then once you down convert them, and before you up convert them, you have analog to digital converters and digital to analog converters. And all of those ADCs and DACs, they receive a digital baseband signal, so you have a digital circuit working behind this. So now a complete transceiver, it embodies different fields of the electrical engineering discipline. If we talk about antennas or any of the passive devices which work in the RF frequencies, that comes under microwave design. So microwave designers, they focus on antenna design, how to improve the gain of antennas, how to improve the directionality of antennas. Then RF circuit designers, they focus on the design of these active components, the design of switches, the design of LNAs, the design of PAs, the design of down converters and up converters, and oscillators as well, right? And then once you have, so let me rub this and okay, and yeah, okay. So there's a switch. Let me draw this again. So there's a switch in between. So there's a switch in between, and now so the RF circuit designer works in the high frequency range, right? So all of these LNAs and PAs and converters and up converters and down converters, they work in high frequencies, maybe in the gigahertz range, right? Then once you down convert those signals, you are moving back into the megahertz or kilohertz range, right? And in this domain, you'll be using analog circuit design, and as you'll see, these are completely different. The requirements are completely different. The terms used are completely different. The way devices are viewed is completely different. And in the analog circuit design, you work in lower frequency domains, and then you have these analog to digital converters, digital to analog converters. And then when you go to digital baseband processors, in digital circuits, they work on a completely different model, right? So till now you had analog signals, now you move back to digital signals. These might be digital signals might be in the gigahertz range, but they're completely different as compared to analog and RF circuits, because these gigahertz signals are just in two forms, right? They are just in square waves. So the principle of operation is completely different, and the way they are designed is again completely different from analog and RF circuit design. So I guess we'll end this lecture at this point, so that as I mentioned, we'll make small videos. So in the next video, we'll continue and we'll talk about the electromagnetic spectrum, and then from then on, we'll talk about the basics or the overview of different topics, which are there in the RF microelectronics domain. Thank you.